When most people think about rockets, they think about fire. Towering flames, roaring engines, and explosive launches dominate our imagination. But hidden behind every successful launch is something far stranger than fire. It is one of the coldest substances humans routinely handle on Earth. Before a rocket ever leaves the launch pad, engineers must produce, transport, store, and manage liquid hydrogen at an astonishing temperature of -253 degrees Celsius. That is colder than Antarctica, colder than liquid nitrogen, and only about 20 degrees above absolute zero. The giant storage tanks, cryogenic pipelines, refrigeration systems, and insulated transfer lines surrounding modern launch facilities are among the most sophisticated industrial systems ever built. Without them, many of the world's most powerful rockets could never leave the ground. In this video, we will uncover why hydrogen must become colder than space itself and explore the hidden infrastructure that makes it possible. Not all rocket fuels are created equal. Throughout the history of spaceflight, engineers have experimented with many different fuels, including kerosene, methane, and hydrogen. Each offers advantages and disadvantages, but when maximum performance is required, hydrogen often becomes the preferred choice. Hydrogen delivers one of the highest specific impulses of any practical rocket fuel. In simple terms, specific impulse measures how efficiently a rocket produces thrust. Because hydrogen is extremely light, the exhaust gases produced during combustion can exit the engine at very high speeds, creating exceptional performance. This is why hydrogen has powered some of the most important rockets in history, including the Space Shuttle main engines and many upper-stage launch systems. The challenge, however, is that hydrogen's greatest strength also creates its biggest problem. It is the lightest element in the universe, which means it occupies an enormous amount of space. To make hydrogen useful for rockets, engineers must find a way to dramatically reduce its volume. Hydrogen's low density creates one of the biggest engineering challenges in the energy industry. At normal atmospheric conditions, a single kilogram of hydrogen gas occupies roughly 11,000 liters of volume. Imagine trying to fuel a rocket using a gas that takes up the space of an entire room. The tanks would be enormous, the rocket would become impractical, and launch costs would skyrocket. Engineers therefore need a way to pack hydrogen molecules much closer together. The process begins with compression, which forces the molecules into a smaller space. However, compression alone is not enough. Even at very high pressures, hydrogen remains relatively bulky. To truly solve the volume problem, engineers must remove heat from the gas. As temperature decreases, molecular motion slows and the molecules move closer together. Eventually, hydrogen reaches a point where it transitions from a gas into a liquid. This transformation dramatically reduces the space required for storage and makes modern hydrogen-powered rockets possible. Turning hydrogen gas into liquid hydrogen requires an extraordinary sequence of industrial processes. The journey begins with compressors that increase pressure and prepare the hydrogen for cooling. The gas then passes through cryogenic heat exchangers, where heat is gradually removed. Specialized refrigeration systems continue lowering the temperature through multiple cooling stages. Expansion turbines provide additional cooling by allowing the gas to expand under carefully controlled conditions. Each stage removes more thermal energy and pushes hydrogen closer to its liquefaction point. Eventually, the temperature reaches approximately -253 degrees Celsius. At this point, hydrogen undergoes a remarkable transformation. What was once a low-density gas occupying thousands of liters suddenly becomes a dense liquid occupying only a tiny fraction of its original volume. This reduction is what allows rockets to carry enough fuel to reach orbit and beyond. -253 degrees Celsius is a temperature that is difficult to comprehend. Water boils at 100 degrees Celsius. Typical room temperature is around 20 degrees Celsius. The coldest temperature ever recorded in Antarctica is about -89 degrees Celsius. Liquid nitrogen exists at approximately -196 degrees Celsius. Yet hydrogen must be cooled even further. At -253 degrees Celsius, liquid hydrogen exists only about 20 degrees above absolute zero, the theoretical limit where molecular motion nearly stops. Very few industrial processes operate anywhere near this temperature. At these extremes, materials behave differently. Metals shrink, seals become brittle, lubricants stop functioning normally, and even measuring temperature becomes challenging. Every component within a hydrogen liquefaction plant must be specifically engineered to survive these conditions. Maintaining hydrogen at this temperature requires some of the most advanced engineering ever developed. Many people assume that outer space is the coldest place imaginable. In reality, liquid hydrogen storage operates surprisingly close to some of the coldest environments encountered anywhere in nature. At -253 degrees Celsius, liquid hydrogen exists extremely close to absolute zero. Maintaining these temperatures requires a constant battle against heat. Heat enters from sunlight, surrounding equipment, the ground, nearby structures, and even the atmosphere itself. Every source of thermal energy threatens to warm the hydrogen and turn it back into a gas. Engineers therefore design storage systems that function like gigantic industrial thermos bottles. Their mission is simple but incredibly difficult: keep heat out and keep hydrogen cold. Achieving this goal requires advanced insulation technologies, vacuum systems, and continuous monitoring. Without these systems, liquid hydrogen would quickly begin evaporating. Creating liquid hydrogen is impressive, but keeping it liquid is often even harder. No insulation system is perfect. Heat always finds a way into the storage vessel. To combat this, engineers build multiple protective layers. The outer shell provides structural support and environmental protection. Inside that shell is a vacuum layer that dramatically reduces heat transfer. Additional multi-layer insulation reflects thermal radiation and further limits energy entering the tank. Together, these layers create one of the most advanced storage technologies in modern engineering. Despite these protections, small amounts of heat still enter the system. As hydrogen absorbs this heat, some of the liquid begins turning back into gas. This process is known as boil-off. Boil-off cannot be completely eliminated, but it can be managed. Modern facilities capture, recompress, reuse, or reliquefy this gas to reduce losses and improve efficiency. Behind every tank of liquid hydrogen stands an enormous collection of hidden machinery. Compressors increase pressure. Heat exchangers remove thermal energy. Refrigeration systems push temperatures lower and lower. Expansion turbines generate additional cooling effects. Liquefaction cold boxes perform the final transformation from gas to liquid. Thousands of sensors continuously monitor pressure, temperature, flow rates, and system performance. Advanced automation systems coordinate every stage of operation in real time. Safety systems remain active around the clock to protect both equipment and personnel. Together, these machines create one of the most complex industrial ecosystems on Earth. While rockets often receive the attention, it is this hidden infrastructure that makes cryogenic hydrogen possible. Without these machines, hydrogen would never reach the temperatures required for modern spaceflight. Liquid hydrogen is much more than a fuel. It is the product of an entire industrial ecosystem. The journey begins with electricity generation and hydrogen production. Electrolyzers split water into hydrogen and oxygen. Water treatment systems ensure purity. Compression systems prepare hydrogen for processing. Liquefaction plants transform gas into liquid. Storage terminals hold cryogenic inventories. Specialized trucks, rail systems, ships, and pipelines move hydrogen across regions and continents. Distribution networks deliver hydrogen to launch facilities, industrial customers, and future energy applications. Every step requires dedicated equipment, specialized expertise, and significant investment. Collectively, this infrastructure often represents billions of dollars in assets. Yet it supports far more than just space exploration. It also forms the foundation of many emerging clean energy industries. The technologies developed for liquid hydrogen are increasingly influencing the future of clean energy. Hydrogen can store renewable electricity for long periods and help balance power grids. It can support industrial decarbonization in sectors such as steel, chemicals, and refining. Researchers are exploring hydrogen-powered aviation systems capable of reducing emissions from long-distance air travel. Hydrogen can also serve as a transportation fuel for ships, heavy trucks, and other hard-to-electrify sectors. In many ways, the cryogenic infrastructure originally developed for aerospace is now becoming part of a much broader energy transition. The same liquefaction plants, storage tanks, pipelines, and transport systems that support rockets may also help power future industries. This connection between aerospace and clean tech demonstrates how advanced engineering often creates benefits far beyond its original purpose. What we have explored today is only one small piece of the hydrogen ecosystem. Behind every hydrogen project lies an enormous network of machines, systems, components, suppliers, and engineering decisions. Electrolyzers produce hydrogen. Compressors increase pressure. Heat exchangers remove energy. Liquefaction systems create cryogenic temperatures. Storage tanks preserve the liquid state. Fuel cells convert hydrogen back into electricity. Understanding how all these technologies connect is essential for anyone interested in the future of hydrogen. That is exactly why we created H2 Hub by Renee Energy. H2 Hub helps professionals, developers, students, and investors explore the machines behind hydrogen, generate project schematics, understand system integration, and visualize real-world hydrogen infrastructure. The future of hydrogen will not be built by headlines alone. It will be built by engineering, infrastructure, and the people who understand how these hidden systems work. Welcome to the machines behind hydrogen.